atmospheric circulation. This is chapter 18, where we'll be talking about circulation cells, prevailing winds, location of high and low pressure zones, and finally a little bit about climatic variation. Of course, we won't cover chapter 20, but if you're interested in thinking about or studying a little bit more about climate and climatic zones, then chapter 20 would be a good place to start with that. The diagram on the right is pretty complicated, and what it's showing us are what we call six circulation cells: the Hadley cells, the Ferrel cells, and the polar cells. The Hadley cell is down here close to the equator. The polar cell is up here, and then the Ferrel cell is in the middle. And these cells are a function of a number of variables that are acting on the Earth and its atmosphere at one time. One of those is the rotation of the Earth and the Coriolis effect. The other is the differential heating between the equatorial regions of the Earth's surface and the poles. At the equator, we know that the equator is getting more sun because it's or getting more radiation from the sun because of its alignment with the rays of the sun, and that at the poles, north or south poles, that the area there is getting less sun, in part because of its alignment, but also because we find that the Earth has seasons in a particular tilt, and so that affects the amount of radiation as well. So we have a lot of sun or a lot of radiation causing air masses to rise up. And if the Earth was not rotating, that air would rise, and then it would head north, and it would sink down at the poles where it cooled, and then cruise along the Earth's surface and rise back up, creating one big circulatory cell. But what we find is we don't have one big circulatory cell, and that's in part because, I'm going to go ahead and erase these guys, that's in part because we have deflection of fluids on the Earth's surface caused by the Coriolis effect, which make things move east-west instead of just north-south. And so those north-south circulation cells get broken up, right? And so that's what's happening here. This break here between the Hadley cell and the Ferrel cell, and this break between the Ferrel cell and the polar cell, or the the polar cell in the north, is caused by the Coriolis effect and the deflection to the right. If we strongly deflect something to the right, it is no longer traveling to the north. And so winds that would normally go up and toward the North Pole end up, they can't make it that far. And so they end up not going like that, but they end up moving off to the right like this, and that ends up creating 3 circulatory cells or in the northern hemisphere, and 3 circulatory cells in the southern hemisphere, and those have strong influence on both the prevailing winds in the region as well as climate. You'll notice that these winds are labeled, and so here we have in the equatorial region, so between about 0 degrees and about 30 degrees south, and we'll come up here to about 30 degrees north, we have the trade winds, and they're named based on the direction that they're coming from. So, for instance, this is the direction they're flowing from towards you is from the northeast, so they're coming from the northeast, and so they're called the northeast trade winds. These are the below the equator in the southern hemisphere, just below the equator, between 30 degrees south and 0. We're looking at the southeast trade winds, so they're coming from the southeast and blowing towards the northwest. If we move from 30 degrees or up to about 30 degrees north or south, and then we move sort of up to about 60, there's another zone or region here, and these are called the westerlies. They're moving from the west, and in this case, from what we call the subtropical high pressure system, and they're blowing from the west here as well, down here in this zone as well, and we cannot see the polar zone that's way, way down here on the Earth. And then at the bottom of the Earth. And then if we come up to the top, we can actually see the polar easterlies, right? So these winds are blowing out of the easterly, out of the northeast, and coming down like this, similar to, notice, the trade winds, the northeast trade winds. So the polar easterlies and the trade winds are blowing in the same direction, and then we have the westerlies blowing in the opposite direction, and that has to do with how these air masses are converging, but it also has to do with the rotation of the Earth and the Coriolis effect. If we look at the distribution of winds across the Earth's surface, we see low pressure and high pressure systems. So here's our, anticyclone down here in the southern hemisphere, anticyclone, anticyclone. Where are those high pressures? And notice when I'm talking about high pressures, we have contoured isobars. So the pressure here is at 1020, 1020, 1020, and then where are those low pressure zones? Well, low pressure zones are sitting over the continents, right? Low pressure means hot, buoyant air. We know that the crust heats up the atmosphere more quickly, and so that ends up leaving us with rising air over the continents, and cooling air, sinking air over the oceans. Now, that's in the southern hemisphere, right? So every circle of high pressure zone I've drawn is in the southern hemisphere, and this is January. So in the southern hemisphere, in January, we're in the summer, or I should say the June or the December solstice. We're in the December solstice, right? It's actually January, so we're just past the December, but we're in that in the period of the solstice, in December solstice, where we just passed it, and we've got higher temperatures, more solar radiation in the southern hemisphere, and so that means that we've got hot rocks, right? Hot rocks create hot air. In the northern hemisphere, what season are we in? Well, we're in so this is summer, right? This is the summer season, and up here in the northern hemisphere, we're in winter. Okay, we're in the middle of winter, and so what do we see? Where do those zones go? Well, those low pressure zones are no longer over the continents, not here. In fact, we see in some cases major high pressure zones moving onto continental land masses. And that's because rocks are cooling down faster than the ocean water, and we're getting cool sinking air over those continental land masses. So let's just reverse this, right? So now we're going into July, so we've gone to the June. We're just past the June solstice. In the northern hemisphere, we are in the summer. In the southern hemisphere, it is now in the winter season. And what do we see happen? Well, we see a high pressure zone here. We see a low pressure zone. We see a low pressure zone forming over North America, or over the U.S. and parts of Mexico. Where have those high pressure zones moved? Well, they've moved over the oceans, right? So air is cooling and sinking out here, and cooling and sinking out here. And so what does this have to do with redistributing Earth's heat? Well, remember, we've got circulatory cells moving air masses north and south. We've got the Coriolis effect causing deflection to the right or to the left, depending on what hemisphere you're in. And then we have these low pressure and high pressure systems, which are moving air vertically. In particular, what we see is an interesting place called the Intertropical Convergence Zone, and that's shown here by this purple line. And you'll notice that it kind of gets deflected in different locations, both north of 0 degrees latitude and south of 0 degrees latitude. During the summertime, in the northern hemisphere, we see that ITCZ gets pushed to the north, north of the equator. And if we back up, notice the ITCZ during our northern hemisphere winter experience, or the January month, or we're in the sort of just past the December solstice, the ITCZ is pushed south of this equatorial boundary, and it really marks where the two Hadley cells are coming together, and we have essentially what is a low pressure here, a low pressure all along this zone. And low pressure means rising air masses. It means lots of rain and high zone of precipitation. So if we take a look at a regional radar map, we can actually see the ITCZ when we're looking at the sort of amount of moisture or amount of rain in a region, and we see that this band of rain here is what we get from atmospheric winds moving like this, atmospheric winds moving like this, coming together like this, and coming together like this. And so we get vertical motion and low pressure. Low pressure at the ITCZ. And so we end up with high rainfall. And you'll notice we're looking at 12 inches down to 8 or even 5 or 6 inches right along that equatorial region. What does this mean? Well, it means globally we get zones that are dry and zones that are wet. Sometimes it has a lot to do with sort of where you're at within the continent. But you'll notice right through the equatorial region across the globe, we see a high zone or a zone of high rainfall that is related to the ITCZ. Now, what we also get are dry zones, and those dry zones are obfuscated or a little bit confusing because we also see some coastal wet zones, but the dry zones typically occur just north of the Tropic of Cancer, so around 30 degrees north. Notice not much rain, especially in Africa and parts of Asia. And then we also get a dry zone down here, 30 degrees south, known as Australia, the tip of Africa here, down into South Africa and Namibia. These are very dry regions. And some southern parts of South America are also dry regions. So this is dry, right? And this is dry, and this is wet. Okay, so we're getting climatic variation. Notice here, major deserts highlighted and distributed across different latitudes. Notice at 30 degrees, I can highlight that a little bit differently. Maybe red's a good color on this diagram. 30 degrees north, and then here's 30 degrees south. We see, just in general, we see bands of dry and bands of dry areas, so we see deserts forming in those regions. There's a number of reasons why deserts can form, including the presence of mountains, and also ocean circulation will affect the formation of deserts. So it's not entirely a linear distribution, but it is strongly correlated with the latitude at which we're at, and that latitude is connected to places where we have low pressure and rising air. So we have, wherever we have low pressure, if you look at the diagram on the right here, low pressure and rising air at the equator means high rainfall, right? Air rises. As it rises, it is expanding and cooling. Cooling drives atmospheric moisture to come out, change from vapor to condense as precipitation. And then what happens is that air moves off to the north or off to the south, so to higher latitudes, and as it's moving, it's cooling off, and eventually it's got to sink back down, and it sinks back down at 30 degrees north and 30 degrees south. Well, when it sinks, it's actually not going to create or deposit any more precipitation because we're actually increasing pressure and we're warming up the air. And if we warm up the air, it means it can hold more moisture. And so whatever moisture it's carrying is sort of trapped there. It's also lost a lot of moisture at the lower latitudes. And so this zone here is dry, right? So this zone here is also dry, and this zone is wet. And that's on a global scale. And so what we find is that most deserts occur around 30 degrees north and 30 degrees south latitude. All right, so if we want to summarize kind of what's been going on here, right, we can take the Earth and we'll draw it. Actually, I think I'll draw this. We'll start it out in a pretty neutral color here. We'll draw half an Earth, and we'll go southern hemisphere, northern hemisphere. We'll add in 0 degrees, and that's our equator. We'll add in 30 degrees, We'll add in 66 or 60. We'll just do 60. That's easiest. Really, the Arctic Circle's at 66.5. And we'll come up to the northern hemisphere and we'll add in our 30 degrees. And we'll add in our Arctic Circle. It's 60 south would be 66.5 south would be Antarctic Circle, but I think you get the drift. All right, and so now we've got to add in our circulatory cells, and we know that at the equator we've got the ITCZ, and that is a low pressure zone. So we got low pressure driving circulation like this, comes around and then comes back down at 30 degrees there. And so we've got also in the southern hemisphere something coming around like this. It sinks back down right about there at 30 degrees south and then comes back over. And so this is a low pressure zone, and it is also wet, right? This is a high pressure zone, and this is a high pressure zone, and is also dry. Okay, so that's our Hadley cell, and then what we have is another circulatory cell to the north and south, looking something like this, circulating down. So again, part of the high pressure system, moving across the Earth's surface, and then up like this, and creating a low pressure zone here, 60 degrees north. So there's not a lot of moisture there, but there's going to be clouds and precipitation. And the same thing over here. High pressure, so we've got air mass moving down, and it moves back out towards the pole along the Earth's surface and back up and circulates something like that. Okay. As far as winds go, and that's also a low pressure system. As far as winds go, in terms of their movement, we have the northeast and the southeast trades. So wind is deflected to the right in the northern hemisphere, so the trades come in like this, and they come in like that. So that's a trade wind. Again, trades in the southern hemisphere. We got the westerlies, again, deflected to the right. And then up here, which is a little bit hard to draw, I've got, again, circulation moving around like this. We got a low pressure zone, so I've got air moving up and then back to the South Pole where it cools, sinks, moves along the Earth's surface and back up. And then we have our easterlies, which are basically parallel to the trade winds. Okay, and so we'd expect rain at the equator. It's dry, 30 degrees south, 30 degrees north, and then more precipitation closer to the Arctic and Antarctic circle. So this is a good diagram to kind of have in your head and keep in mind for sort of global circulation and how it's organized. I'll be moving on to sort of wrap up talking about more of a regional process called the Southern Oscillation Index, and that will lead us into a conversation about El Nino and La Nina, which are climatic variations that are a little bit hard to predict. We're working on it, trying to understand them, but they occur every sort of 2 to 7 years, and the National Oceanic and Atmospheric Association is still working on sort of understanding those climatic variations and helping us to sort of predict them by reporting on changes in sea level, sea surface temperatures, wind strengths, and atmospheric pressures, which we'll talk about later.